Okay, today I'm very happy to announce that this will be our last new lesson of the year. That makes me happy, and also there's a little bit of sadness involved. The lesson itself is broken into a couple different parts. However, I will mention that the first part of this lesson is fairly easy. However, it does get a little scary at the end, so I'll try to make it as painless as possible, even though it will cause you some pain. This is something that once I start getting into it, you will probably ask yourself, why didn't we do this earlier in the year? Because it involves limits. And the answer to that is because we didn't have all the other things we needed to do this. So what is this? This is something called the hospital. French mathematician L'Hôpital, which literally translates to the hospital. So his last name was the hospital, which is pretty cool. And he came up with this little idea, which for us is pretty profound. So we're going to start with a limit. It's been a while since we've done limits, so I'll guide you through it. But we're going to take the limit as x approaches 0 of 3 times the cosine of x plus 5x minus 3 all over 2x. Okay, quick review. What's the first thing you always do in a limit problem? Plug and chug. So do that, please. I'll wait. Yeah, you're in an awkward spot. You gotta turn around or look at me, get out of the way. Whatever works for you. I can just get out of the way too. Yes, you do. So proud. How about that top?
3.
No, it would still be
0.
0.
I thought cosine was 1.
It is.
3 minus 3.
So, let's take this in stages. The first thing Ryan said was the denominator is 0, which is correct, because 2 times 0 is 0. Very good, Ryan. When we did limits, however, we would then stop there and start to panic. Well, what could we do next? We could algebraically manipulate. We could simplify the top and the bottom, cancel things, do all this other gunk, because this is undefined. However, if you plug and chug like you were supposed to, you would see that this is 0 over 0. I think we've had this conversation before, but it'll be fun to have it again. What's 0 over 0 equal to?
1.
Why, Bella?
Where was that right?
I didn't say you were right or wrong. I'm just asking what your logic is. I'll say this. There are a number of people in here that would agree with you that it's equal to 1, and I'm asking you why you said 1.
Because the top is equal to the denominator.
Anytime you have a fraction when the numerator and denominator are equal to each other, the value is 1. 7 over 7. Negative gabillion over negative gabillion is 1. Very good. Other answers?
Error.
Noah.
Undefined.
Undefined. Because?
Anything. Well, you can't divide anything by 0.
Excellent. And the other possible answer?
Error.
0. Is that you doing it?
No.
Who said 0? Sorry, Jack. Why?
Is the
Numerator is 0. Good. 3 possibilities all have a logical explanation. Which one's correct? All of them or none of them, yeah. So we're not even going to bother talking about it. We just know that that's bad. This is what's called an indeterminate form. Most of the lesson today is going to be looking at different indeterminate forms. This is the easiest one to deal with. Yeah, there's a ton. We're just going to look at about 4 of them, maybe. Okay, the last one, not so much fun. Okay, so when we did limits, we would stop then. This doesn't work. We can't algebraically manipulate the top or the bottom. We can't do it. Does not exist, and we're done. However, with L'Hôpital, what L'Hôpital realized and wrote a rather lengthy proof about is he came up with a fancy schmancy theorem. So I'm going to write down the fancy schmancy theorem just so you can see it, but then I'll also explain it to you in English. Yeah. There's a much easier explanation. So why put this one? Because I'm paying some respect to Mr. L'Hopital, who, well, he's dead, he doesn't really care. But anyways, just showing some respect for the masters.
That's G prime effects on the left.
Yes, yeah, you're right. I got a little excited there and just went crazy. All right, in English, what that means is when you take a limit and you plug and chug, if you get an indeterminate form, take the derivative of the top, take the derivative of the bottom, and do it again. Okay? Simple. Now, notice I said take the derivative of the top and the derivative of the bottom, not the derivative of the whole thing. We're not doing quotient rules here. Okay, it's easier than that. So shrink this guy, put it up here, and finish this problem. 0 over 0, indeterminate form. Check. Let's move on. L'Hopital says then, take the derivative of the top, Lexi, what's the derivative of the numerator? And the bottom, please? 2. And do it all over again. So plug in x again. Sorry, I lied. Plug in 0 again. The sign of 0 is?
0.
0. So therefore we get an answer of 5/2. Done. Problems? You can't just start throwing around L'Hopital's rule all willy-nilly now. You have to check to see if it's an indeterminate form. So you might be asking yourself, what are the other indeterminate forms? Well, it's funny you should ask. I have some others for you. Let's try this guy. Whoa. Approaches infinity of the natural log of x over square root of x. It's been a while since we've talked about the natural log of x. You might want to refresh your memory on what that graph looks like. It'll help you figure out the limits. What happens when x gets very big in the natural log of x? Say again? No.
It gets closer to 0.
No. Infinity, correct. Quick refresher, the graph of the natural log of x looks something like that. X gets very big, it goes very big. And so therefore, the numerator is infinity. What's the square root of infinity? Infinity. Oh, another indeterminate form. Woo! Infinity over infinity.
Wait, why is the denominator infinity?
What's the square root of infinity?
Oh, as x approaches it.
Yeah. Okay. So we could go through the same argument we had, not argument, but discussion about 0 over 0. What is infinity over infinity equal? Well, it could be 1 because it's something over itself. It could be 0 because if the denominator of a fraction gets very, very big, the fraction itself approaches 0. It could be infinity because the numerator is getting very big, so therefore the fraction must go to infinity. None of that applies. We just know that that's another indeterminate form. Therefore, L'Hopital's rule applies. Quick refresher here. What's the derivative of the natural log of x? 1 over x. Beautiful. Square root of x to the 1/2, bring the 1/2 down, reduce it by 1. If it helps, not if it helps, it would help to rewrite this bad boy. And I don't want to plug and chug yet, I'd like to simplify that a little more. Dividing by a fraction, same thing as multiplying by the numerator. Okay, so this becomes the the limit as x approaches infinity of 1 over x times 2 over the square root of x over 1. Which becomes natural log as x approaches infinity of 2. How does this, let me change colors here. How does this simplify? How do you deal with those x's?
Subtract the exponents.
Good. So what would it become?
-1/2.
Good. Which gives us this. To make your life a lot easier, it's worth doing the algebra to simplify those things before you take the limit. Now we know we're going to get a value. How do I know I'm going to get a value? Because I no longer have a variable in the numerator. That numerator is always going to be 2. So if the numerator stays the same and the denominator gets very, very big, what happens to the fraction? In other words, what's the answer to this problem? 0. That's an important concept. Does anybody need that reviewed? Okay. 1/2, 1/3, 1/8, 1/10. 1 millionth. Question here in the front.
I have a separate question about
The person or the problem? For the theorem?
the theorem.
You don't want to know about him personally?
I don't know.
Good, because I don't know anything about him.
Great.
He was French. I do know something. I lied. He was a male.
This
What if
last
he's watching? Where would he be watching from? Oh, yeah, well, that opens a whole new can of worms, which we don't want to go down right now with me. Go ahead, Noah. He would probably be
Are we
upset.
going to know how we got to f prime of x over g prime of x, or do we just leave it as like, this is something that you know?
Well, it's something you just have to learn.
Okay.
The proof of it is not easy.
Uh,
So I skipped that because we don't really need to know that.
Right.
Okay. Good question. All right, anything else? Oh, good, we're not done yet. On this problem I meant. Okay, turn the page. Let's try another one. Ooh, this will be a good review. Let's try the limit as x approaches infinity of e to the 3x over x squared. All right, you try this one on your own. I'll walk around and assist.
I'm sorry, what? Oh, it's e to the x would be the exact same thing, but then you have to add on the change. So it's e to the 3x over So what do you do?
Can you do it again? Remember the derivative of e to the anything is itself.
Oh, okay, thank you.
Yeah, okay, so 3x, E3. So it's just 3. No, wait, isn't the 3x still there? Yeah, it's E.
All righty, let's see what we got. So, first things first. I know that we're talking about L'Hopital's rule, so some of you probably just dove right into it. But you need to determine, this sounds silly, you need to determine if it's an indeterminate form. Yeah, that's proper English. Okay. Infinity over infinity. Are we good to go with that?
Yeah.
Good. Indeterminate form, we're good. The hospital applies, so now we go crazy. Some of you are having trouble remembering how to take a derivative of e to the 3x. I'll help you. 3e to the 3x. Itself times chaining on the derivative of the numerator, and the bottom you shouldn't have had any trouble with. Then some people vapor locked on this. What do I do now? What happens? You get infinity over infinity again. So the question is, what do? Can I just keep going? The answer is yes, because think of this as a whole new problem. If I just gave you the second line and said solve the problem, you would apply L'Hopital's. This tells me I can apply L'Hopital's. Do it again. As you get deeper and deeper into these problems, you will see that there are certain mathematical functions that never go away. Now, what I mean by that is, no matter how many times I take a derivative of the numerator, there's always going to be an e to the 3x there. Okay? The only thing that's going to change is that number in front. So now the next derivative becomes e to the 3x. Sorry, 9e to the 3x. All of a sudden, however, the denominator changes into a constant. No longer an undefined term, and in fact, we don't even care. We're going to plug and chug. As x goes to infinity, what happens to e to the 3x? It becomes infinity. If the numerator gets very big, what happens to the entire fraction? It becomes infinity. So that is the correct answer. Okay?
Is that not an indeterminate form?
Infinity?
Yeah.
No. Just infinity is not an indeterminate form.
Yeah, I know, it says infinity.
Yeah, but like the indeterminate is like it can, there's like 0, 1, or like infinite or like undefined. So with this, it's just infinite.
We know what infinity is. It's just a big honking number.
All right.
0 over 0 could be 1, could be 0, could be undefined, could be a trainer.
Also, in this theorem,
You keep thinking about the now,
Yeah.
don't you? Yep. Yeah, I'll break you up with that.
the theorem that we wrote, in the theorem that we wrote, where does it say that 0 over 0 can't be? Like, I'm reading it over and over and it doesn't feel like 0 over 0.
Don't obsess on the blue stuff.
Doesn't matter. Just indeterminate. Okay.
We call that, no, we'll never. Just let it go. Okay. Any problems so far? Those are the two easy ones. And they're also the ones that you'll see 75% of the time when L'Hopital's pops up. There are some others, though. The chances of you seeing them are slim, but in order for me to do my job adequately, I want to show it to you at least once, so that if it does pop up, I can at least raise my hands and say, I did what I needed to. I know. We call that CYA. Okay, so we're going to start with this. If we have f of x times g of x, I can rewrite that. Now, this is going to seem silly. Why am I doing this? You'll see once all the puzzle pieces fit together. This is the same thing as f of x over 1 over g of x, or, what the heck? Hold, please. My board's freaking out. Come on. There we go. Bingo. Okay, so f of x times g of x is the same thing as f of x over 1 over g of x, or g of x over 1 over f of x. And again, who cares? Just be patient for a second. Because we want to look at our next indeterminate form, which would come up in the following problem. Like all limit problems, plug and chug. When I plug and chug, what is the limit as x approaches 0 for the natural log of x? Anybody? Go. Why?
I'm not sure why, but I just know that I want to 0.
And if natural log is 0, it has to be bigger than 0 for a natural log.
Okay. So what if it's just a little bit bigger than 0? Bust out your calculators, graph the natural log of x. Not the whole function, just the natural log of x. We'll deal with the x squared in a second.
It can be slightly larger than 0.
Yeah, so just to the right of the y-axis. I love how everybody's looking around the room at others like, you say something. I'm not saying something. You say something. No, you say something.
Question.
What's that when x approaches 0?
Oh.
Somebody take a chance.
Doesn't make sense.
What?
Doesn't make sense.
Why?
Because
The limit's not.
it goes you just said it to the right of it because it intersects at 1, the x-axis. So
Correct. So what happens when you go further to the right, towards the y-axis?
it's gonna grow. No. Yeah.
Yeah. No. Yeah.
Yeah. I don't know.
Anybody else? Alan?
Well, aren't we
Yeah.
gonna be multiplying it by 0 either way because of x squared?
Oh yeah. Well, we can do that first part. That's easy. That's 0. But I still want to know. I still got to know what the second part is. Because if it's 0, or if it's 9, or if it's 14, I'll get 0. then that's not L'Hopital's, and you know it's not gonna be something pretty because we're doing L'Hopital's. So you know it's gonna be something bizarre, right?
Is it 1 over 0?
Isn't it like infinity because it can just keep getting infinitely smaller but not like negative or 0?
Kind of. What's the graph look like? Somebody describe the graph to me, please.
It's looks like an exponential.
You look like you're walking like an Egyptian. From 1, you said, right?
Yeah.
And it goes up like that. What happens over here?
It dips a
Just
little
goes
bit.
infinitely down too, and it never touches.
No, it says, no, it says air.
Huh?
I can,
Wait, doesn't it?
It's fine.
Yeah,
It's
mine
not
does.
bad.
Maybe your calculators aren't graphing it adequately enough.
I feel like it is.
Oh, you're using that.
Oh,
it
no.
doesn't go all the way
Like
down.
after like -2.
Well, yeah, but that's
Oh, wait,
because it's
mine-
not like, you're not seeing the part where it's like 0.0.
Yeah, you can't. Yeah, okay. I understand the confusion now.
I'm telling you.
I get it. If you pull out your iPads and graph it on Desmos, you'll see it should look something like that. Well, that took a lot longer than I expected.
You'll never stop moving.
Okay. Negative infinity. So I understand the problem in that you were looking at it on the calculator and it kind of looks like that. Right. Did one of you say it back there?
It looks like this.
Well,
Sorry, my bad.
don't be afraid. The worst that could happen is we just make fun of you. Indeterminate form. It's one of our new ones. So how do we handle this? Well, this is where the stuff in pink becomes relevant. In order to actually find the limit of this, we're going to turn that product into a quotient. And you have to decide which one do you want to send to the bottom. You can send either one. I usually send the one that I'm less scared of. I'm less scared of the x squared, so I'm going to send that to the bottom. Could we do the natural log of x? Yes. But I find it's usually easier when you do it this way. Okay, so far. Algebra. Then we go through the whole process again. We've already beat a dead horse here. That's negative infinity. Now, what's 1 over 0 as you get really close to 0? 1 over 0 undefined, but a limit as the denominator approaches 0. We talked about already. It goes to infinity.
Oh.
An indeterminate form. By the way, infinity over infinity, same thing as negative infinity over infinity. It's still an indeterminate form. Okay, so far.
It wouldn't be negative infinity?
No, because it's getting infinitely smaller. So you're dividing like 1 by an infinitely small number, so it'll get bigger. Like a decimal.
Alright, I'll give it a second. Sure. It'll click later, yeah.
How much later? June?
Tomorrow.
Good. Let's try to get it to click before May 4th.
Before May 4th.
Okay, good, thanks.
I like math.
Okay, so after all of that fun stuff, we get a new indeterminate form. We turn that weird indeterminate form into a fraction. Now we get an old indeterminate form, so then we apply the hospital to it. What's the derivative of the natural log of x? Good. Okay, that was a big jump for some of you, I know. But that's what you'd get. X to the negative 2. Oh, no, it's not. That's what you'd get. Bring the negative 2 down, reduce it by 1. Goes back in the denominator. Simplify 1 over x times x cubed over negative 2. The limit as x approaches 0 of x squared over negative 2. After all of that gunk, we get 0. On the AP test itself, you will probably not see a L'Hopital's problem on the calculator portion, because if they did do that, all you'd have to do is just graph the original function and see what it approaches as x gets close to 0. So what they're going to do more than likely is give it to you on a non-calculator portion, so that you have to grind it out using L'Hopital's. 0 times infinity. 0 times negative infinity. Our third indeterminate form. Okay, how are we doing so far? Okay, remember the third one you turn into one of the first ones, we're good to go. The last one's not so much fun. Actually, I have 2 more. I'll save the bad one for last. The other one is scary looking, but is very easy to solve, because all you're going to do is use some algebra. Let's suppose I have the limit as x approaches infinity of 1 over e to the x minus 1 minus 1 over x. The light bulb went on, huh?
Yeah.
Good. Makes me happy. I'm going to speed up the process a little bit here. If and when we plug and chug, we'd get infinity minus infinity. That's that. Indeterminate form, we could go through a similar argument. What's infinity minus infinity? Well, it could be 0, because anything minus itself is 0. It could be indeterminate. The only thing you're going to do with this find a common denominator, do some algebra. I'll do it quickly so you can see it, but I'm not going to spend a lot of time on it, because you should be able to handle this algebra. And after all that fun, you'll get 0 over 0 in this particular example. And now you see the pattern here. Common denominator algebra gets me into a form that I can work with, which is a 0 over 0. Sometimes you get infinity over infinity. And then you just go down that hospital rabbit hole again. Take the derivative of the top, derivative of the bottom. Life is grand. Notice when you take the derivative of the bottom, you're back to the old product rule. Even if you multiply it out, you still have a product rule, because you have x times e to the x. I'll spare you that pain. Follow that now? That's number 4. Number 5, not so much fun, but I'm going to make sure we're good to go on this. Oh, yeah, there you are. Yes.
Does the plus rather 0 mean it's moving to the right?
Yeah.
Okay.
Staying on the right side of the 0 value.
All right.
Okay? All right, last one. And this one's not so much fun. And this will summarize a couple different indeterminate forms. So I'll list them all for you. We'll just go with that for now. Okay. Let's flash back a little bit. When we were talking about taking derivatives, we looked at the difference between 3 scenarios. A variable raised to a constant. Taking the derivative of that should be ridiculously easy at this point in time. A constant raised to a variable. A little trickier, but I've shown you how to do that. Remember, that one involves natural logs and stuff. And then the other weird one was the variable raised to a variable. We used logarithmic differentiation with that, which I know you all enjoyed tremendously. We're going to use a variation of logarithmic differentiation to be able to solve a limit involving a variable raised to a variable. So the example I'm going to take you through is what happens when we take the limit as x approaches 0 of x to the x. Get this out of the way. And I'm going to be pretty loosey-goosey with this, meaning I'm going to show you the process, and then we're going to get to the end, and I'm just going to give you like a summary of how to finish the problem. If you want to process where that comes from, I can help you with that later, but for now, I just want to get through it. Okay, so I'm going to start by rewriting the function this way, by just saying, I'm going to wait on the limit for a second. I'm just going to start with the function y equals x to the x, and then do some logarithmic stuff. Okay, so you recall when we did logarithmic differentiation, we took the natural log of both sides, then we applied the log properties, then we went and took the derivative of both sides. I'm not going to do that. Instead, what I'm going to do is take the limit of both sides. I can do that. Whatever you do to one side of the equation is okay as long as you do it to the other side. Problem so far? Good. I'm going to leave the left-hand side alone. Just let it sit there for a while. And I'm going to work with the right-hand side. So I'm going to find the limit of the right-hand side. In fact, I think I'll change colors for that. And let's see, shrink this and move it up there. Okay. So I want to know the limit of that. Well, first things first, I plug and chug. We've gone through this already, and this is 0 times infinity. Okay, so it's a similar problem to what I did in the last one, or the one before. I'm going to turn this into the limit as x approaches 0 of the natural log of x over 1 over x. Because again, I'm less scared of the x, so I send that to the bottom. This gives me, what does that give me? Infinity over infinity. There's a minus sign in there. But, okay, so there, we're happy. Okay? Doesn't matter, it's the same thing. L'Hopital's. Over x times x squared over negative 1, which is, that'll cancel with that. Whoops, no, you get out of the way. With that, and so I get 0 after all that work. Now, this is the part that really screws people up when these do show up. That's not the answer to the problem. That's the answer to this. And so I can go into this lengthy explanation of how you get the final answer. I'm going to just list 3 possibilities. Okay, and they are the following. If Okay, we're going to use that as a key. It's a little hard to see. I'm sorry, I'm going to slide this around like crazy. But notice what happened. We took the function, the x to the x, and wrote it as y, and then we took the limit of both sides. So when we solved all of this stuff on the right, we got this thing, underlined in blue, equal to 0. Well, that thing underlined in blue is this stuff listed on the left-hand side of the legend. And we got 0. Well, 0 is a number. By the way, what does L stand for? You'll recall when we did limits, capital L stands for the numerical value of the limit. 0 is a number. Since 0 is a number, then the final answer of what we're looking for, this is the limit of that original function that we started with, is going to be e to that number. Therefore, going all the way back to here, this is going to be equal to 1. Because e to the 0 is 1. And I'm being a little vague and obtuse here of where these numbers come from, or where this application comes from. But the explanation of where those answers come from is really not worth our time. In that small niche of 25% of the weird indeterminate forms that you get to, probably 5% of them would be a constant or a variable raised to a variable. Of those 5%, probably 95% of the 5% are going to be the first one in red. Okay? Questions?
Is that an L of the E?
That is an L, yes.
That makes sense.
That's why we got 0, because e to the 0 is 1.
Yeah, I thought that was 2.
No, that's an L.